Great. Good morning, everyone. This is paper session 5. So it is indeed a hybrid, short and long talks. We're going to have 3 virtual talks first, but the presenters will be available online for questions. So please prepare your questions for them. We're going to have 5 talks, then a Q&A session. So the first talk is going to be Embodied Multi-Agent Task Planning from Ambiguous Instruction.
Multi-agent task planning from ambiguous instruction. In human-robot collaboration scenarios, instructions given to robots are likely ambiguous, as humans always omit some information in instructions. Meanwhile, the visual perceptions of robots are updated continuously. In the task planning process, multiple robots need to reason the missing information, dynamically decompose and allocate subtasks based on their visual observations to complete the task collaboratively. So we want to tackle these challenges in this paper. We propose a multi-agent embodied task planning framework, develop a learning method which is effective for both simulation and real-world scenarios, and we perform evaluation experiments with newly built benchmark datasets in both simulation and real world. We propose a new framework. Given a high-level ambiguous instruction, missing information and subtasks are generated based on knowledge reasoning, and then subtasks are allocated to a group of agents. With the change of visual observations, agents need to dynamically adjust the task decomposition and allocation results to complete the whole instruction as soon as possible. We construct a new benchmark dataset based on offer-it. We propose 3 types of tasks, and in each type, there exists the implicit receptacle that needs to be reasoned in the ambiguous instructions. We also generate the expert demonstrations for model learning. There are 4 modules in our proposed model. The scene encoder extracts the semantic scene features based on the pre-training method. The task planning consists of decomposition and allocation parts. The task decomposition part dynamically enforces the implicit receptacle and generates the subtask sequence. The task allocation part dynamically allocates subtasks to each agent based on their predicted distance to target objects. The communication module exchanges the information among multiple agents based on the multi-head attention structure. And the action module predicts the next sub-goal for each agent and generates low-level actions. We use imitation learning to train the whole module. The semantic perception and sub-goal prediction bridge the gap between the simulation and the real-world scenarios. In our experiments, we have easy and hard settings in both simulation and real world. In easy setting, targets and agents are in a single room, and in hard settings, targets and agents are distributed in different rooms. We compare different task planning methods, and our model with dynamic task decomposition and allocation method achieves the best, except for Oracle methods. And we compare multiple agents with single agent methods. Our model with multi-agent method achieves better results. We will show qualitative results in both simulation and real-world environments, in both easy and hard settings. In this easy task, the instruction is put the cup away. The carbonate is reasoned to be the receptacle. Based on visual observations, subtasks are reallocated. In this hard task, the instruction is clean the plate and put it on the desk. The sink is inferred to be the receptacle. Based on the visual observations, the agent 2 finds that the desk is in another room, then it enters another room and completes the task. In the real-world scenario, the instruction is freeze a bottle of water. The fridge is inferred to be the receptacle. they find the bottle and the fridge, and finally the bottle can be put into the fridge. In the hard setting, the instruction is bake the apple and put it on the dining table. The microwave is inferred to be the receptacle. After they find the apple and can put it in the microwave, the agent 1 needs to put the apple on the dining table, and it knows from the agent 3 that the table is in another room. Then it goes to another room to find the dining table. That's all. Thanks for listening.
Great, and the next virtual talk is going to be Data Augmentation for Manipulation from the University of Michigan. Peter Mitrano.
And I'll be discussing our paper titled Data Augmentation for Manipulation. In this work, we propose a data augmentation algorithm to increase data efficiency for learning robotic manipulation. Data augmentation has been used to great effect in computer vision. For instance, in an image classification task, we can sometimes apply random rotations or crops to the input without changing the class label. Prior work has shown that models trained on these augmented examples generalize better than those trained without augmentation. However, these methods are specific to both data type and task. Although there are well-established augmentations for image and text, the same cannot be said for robotics. We aim to augment trajectories of geometric state and action data. This includes data like object poses, joint configurations, voxel grids, and point clouds. Furthermore, we focus on short trajectories where some objects in the scene and/or the robot are moving. Additionally, we demonstrate the proposed method on both classification and regression problems. I will now describe our proposed augmentation method, then present our experimental results. The correctness and efficacy of our method is subject to the following assumptions, which are discussed further in the paper. At a high level, our method produces augmentations by applying a rigid body transformation to objects in the scene. Specifically, we divide objects in the scene into 3 categories: the robot, the moved objects, and the environment. We frame augmentation as the following optimization problem, where we consider 3 terms: validity, relevance, and diversity. We define an augmented example as valid if it obeys the laws of physics. Augmentations are relevant if they are similar to data that would be seen when performing the target task. Diversity is maximized when the transformations applied to a given example are uniformly distributed. Given this abstract problem, we then define a tractable approximation specifically for robotic manipulation. This approximation contains 6 objective terms, weighted by parameters beta 1 through 4. The first term expresses diversity as the distance to a uniformly randomly sampled target transformation. The next 4 terms define validity and relevance for the moved object state. These terms encourage the object to remain within the workspace bounding box, penalize invalid transformation parameters, and preserve contacts and near contacts with the environment. The final term defines validity for the robot state, which preserves contacts the robot makes with the scene. We solve the optimization problem by splitting it into 2 parts. In part 1, we optimize the validity, relevance, and diversity for the moved object state. In part 2, we optimize the validity of the robot state. We evaluate this approach with 2 simulated experiments and 1 real-world experiment. First, we evaluated augmentation on a simulated bimanual rope manipulation task, shown here. The robot is holding the ends of the rope and is tasked with placing the middle of the rope within the goal regions under the hooks shown in purple. The planner uses an imperfect model of the rope dynamics, and in order to find accurate plans, it uses a learned classifier which predicts when the dynamics model is accurate. We apply data augmentation to the training data for learning this classifier. We compare against a baseline without any augmentation. Initially, both methods fail to reach the goal, but the method using our augmentation succeeds earlier and more often. If we analyze the success rates averaged over the final 10 iterations, we find that without augmentation, the success rate is 48%, but with augmentation, the success rate is 70%. Next, we evaluated augmentation on a simulated cluttered planar pushing task. The robot's end-effector is shown as a pink cylinder, and the red cylinders are the objects being pushed. We apply augmentation to the training data for the dynamics model. The predictions of the trained model are shown in blue. Note how the predictions with augmentations have less drift, less penetration, and are closer to the true positions. Finally, we also evaluated our method on bimanual rope manipulation in the real world. The scene here is a mock-up of a car engine bay. The robot must move the rope and place it under the engine without snagging it to set up for lifting the engine. To track the rope, we use CDCPD2. We ran 30 iterations of learning, then froze the models for evaluation. Without augmentation, it succeeded in 7 out of 26 trials, and with augmentation, the robot successfully placed the rope under the engine in 13 out of 26 trials. In summary, we propose a novel method for data augmentation for robotic manipulation. We frame augmentation as an optimization problem and show in 3 experiments that training on augmentations improves performance on downstream tasks in the low data regime. Thank you.
Great, and our third virtual talk is bridging model-based safety and model-free reinforcement learning through system identification of low-dimensional linear models from UC Berkeley.
Hi everyone, I'm Zhongyu. I'm going to present our work on bridging model-based safety critical control and model-free reinforcement learning through system identification of low-dimensional linear models. So a year ago, we leveraged reinforcement learning to develop a working controller for a biped robot Cavarsi. It enables the robot to reliably track different walking velocity and walking height in experiments. And it also shows notable robustness when the robot is applied random perturbations. So such robustness actually creates interesting questions. That is, where does this robustness come from, and whether we can formally assess the stability of such an IO-based controller. So if we take this closed-loop system as a new open-loop system with commands as an input, now the input has 4 parts: the desired statutory walking velocity Vx, lateral walking velocity Vy, walking height Z, and turning rate theta. The output is the robot's actual walking velocity and walking height. So can we find an explicit model to describe such closed-loop dynamics? Although it sounds challenging, we can use traditional system identification to tackle this problem. So let's take statutory walking velocity as an example. The input compares the step input, the ramp input, and the chop signal, which is a swipe frequency sine wave. We can measure the robot's actual Vx using the MLP policy we just developed, and we can also test on different policies with different neural net structures. So by looking at the input-output pairs, we can obtain the system step response, the ramp response, and the frequency response. So let's take a look at how does this identification look like. The red line is the system input, the black one is the robot output, and the blue line is the predicted result using these identified models. This actually shows quite good prediction accuracy. Sensing happens in other dimensions, such as the lateral walking velocity, walking height, and turning rate. We find that a linear model is good enough to describe the closed-loop dynamics in each dimension. So since we obtained the explicit model, we can apply some stability analysis on it. We find that all the zero pools are on the left-hand plane, which means that each dimension is asymptotically stable and the minimum phase. This can actually give us some insights about the reason of the robustness using this IO controller. This is only a single controller. We will validate this on different IO policies. The linearity exists among all of these policies except this one. Just using the eyeball test, you can tell the nonlinearity still exists, even when forced to fit a linear model. This is because this policy is not well trained. So the linearity can be a potential metric for the convergence of IO. Moreover, we find this cutoff frequency. If the input frequency exceeds this value, the linearity is not well preserved. So this can actually be a good guidance for the control design if we want to use this closed-loop system. This system has 4 inputs and 4 outputs. So we further show that this is decoupled under a low-frequency input. So this finding is actually a big surprise, because when we explicitly write down Cavarsi's 4-order dynamics, we obtain a huge file. Now, when we use an IO controller, it gives us a simple linear system. It is stable, decoupled, and the minimum phase. So this idea resembles a feedback linearization controller. So is it possible that the model-free IO learns IO linearization unconsciously? So this is a very preliminary work in these directions, and there are lots of questions we cannot answer. But this is a very interesting and open questions we want to bring up to the community. Before solving this theory question, we can actually apply what we found in the safety critical task. Now we use this IO policy, and this closed loop system becomes a new open loop system, but a linear system. And we use this linear model in a higher level safety critical controller, namely the MPC with control barrier functions, to provide safety guarantee in the task where Cavarsi navigates in high constraint environments. This is a joint simulation. Cavarsi is using the proposed method to check the global path while avoiding obstacles nearby. When the robot sees a high constraint environment, the robot will crouch down and travel underneath this space. And after the robot travels through this, it will quickly recover to a normal height and accelerate to the goal while stopping in front of the obstacles. So in conclusion, we propose a new direction to bridge the model-based optimal control and the model-free reinforcement learning by looking at the closed-loop dynamics controlled by IO policy. This can combine the advantages of both sides. We let IO to wrap up the high-order nonlinear dynamics, and it can give us a linear model. And we can use model-based method to provide safety guarantee on top of it. And it can be more practical to use because we have a linear model. Okay, thanks, and happy to take questions.
Yeah, now we're going to switch to a live presentation for a short talk. So Richard Wren from Carnegie Mellon University will discuss a local optimization framework for multi-objective ergodic search.
Hello, everyone. I'm Richard Wren, a PhD student at Carnegie Mellon, and very happy to share our work, a local optimization framework for multi-objective ergodic search. So we are motivated by search and rescue. Let's consider a hazardous material warehouse with leakage. We want to deploy a mobile robot to cover the red area to find the leakage sources, to cover the blue area to find survivors, and stay within the green zone to stay with communication to a base station. So with this motivation, we formulate the following multi-objective ergodic search problem. So the goal is to compute a control for a dynamic robot with some dynamics so that the resulting trajectory can simultaneously cover multiple information maps. Here, each information map is basically a probability distribution that encodes one type of information. To measure the quality of a trajectory, we use an ergodic metric. A trajectory is ergodic if the amount of time spent along this trajectory in a region is proportional to the amount of information in that region. So now, given m information map, we can compute m ergodic values, and put them together, we get an ergodic vector, where each component in this vector corresponds to an objective to be minimized. And since we're optimizing multiple objectives, in general, there does not exist a single solution that can optimize all the objectives at the same time. Therefore, we seek to find a set of Pareto optimal solution. A solution is Pareto optimal if we cannot improve over one objective without deteriorating at least another objective. Okay, now to compute a set of Pareto optimal solution, in this work, we're going to take a weighted sum-based approach, which will appear in the next slide. Okay, to begin with, we will sample a weight vector from the weight space. Here, the weight space is the first quadrant of a sphere subject to the L1 norm, or more intuitively, it's a m-1 dimensional simplex. With the sampled weight vector, we can now take the weighted sum of the information map to get a scalarized information map. And now, with the scalarized information map, we can run existing single objective ergodic coverage algorithm to compute an ergodic trajectory. And the ergodic vector of this trajectory is basically a point in the objective space that approximates the Pareto optimal front. And we will run this iteratively. And actually, with some derivation, we realize that the ergodicity with respect to the scalarized information map is actually a convex function in the Fourier coefficient space. So this motivates us to run local optimization to expedite the computation. So first, we're going to run breadth-first sampling for the weight vectors in the weight space. And second, we're going to cache the pre-computed trajectory, the previously computed trajectories to warm start the subsequent ergodic optimization process. Okay, and then to further expedite the computation, we're going to take a deeper look into the weight sampling procedure. So the basic approach is to directly sample from the weight space, but this approach cannot take the similarity between information maps into consideration. For example, if two information maps, 1 and 3, are similar to each other, then we can simultaneously cover them well at the same time. And we don't need to sample a lot of weight vectors to capture the trade-offs. And like if two information maps are different, then probably we need a lot of weight vectors. So with this idea, we propose the following approach. We're going to first compute the pairwise ergodicity value between each pair of information map, and then use them as the edge length to construct a transformed weight space. And now we're going to sample from this transformed weight space, which can be affinely mapped to the original weight space, which can then be used to scalarize the information map. Okay, next I'm going to show a video that visualizes the entire computational process. Okay, to begin with, we sample from the transformed weight space, get a scalarized information map, run ergodic coverage that is warm-started, and eventually we will end up with an approximated Pareto optimal front. Okay, due to time limit, I have to skip the numerical results, but the short message is that our approach can run up to 3 times faster than the baseline approaches. And our code is also available online. I'm happy to take questions in either the QA or the poster session. Thank you.
And our fifth short talk is by Christian Lanneker from ETH Zurich. Area layouting, design and control of a compliant and actuated end effector for precise in-flight marking on ceilings.
So, hi everybody, my name is Christian. I'm from the Autonomous Systems Lab from ETH Zurich. And in this short talk, I would like to show you some of our more recent work where we designed an end effector for aerial vehicles that can precisely mark points and lines on ceilings so that we can use it for layouting on construction sites. Layouting is basically a step before any fabrication is done. It mainly involves just marking points and lines on ceilings to indicate where to place drywalls or drill holes, for instance. So nowadays, this is still done manually and takes up quite a bit of time, and it's repetitive, especially on big construction sites. Additionally, if you want to do this on ceilings, you have to put up scaffolding, requiring more time. So we thought this could be a nice application for drones to automate the whole process. There is a key challenge to this, though, and that is that for layouting, you have to be very precise, and this is still something that drones are not very good at nowadays. So we asked ourselves if we can actually design an end effector for aerial vehicles that can achieve such a high precision so that we can use it for layouting, and if we can do this in a way such that the end effector is forgiving enough so that the precision of the aerial vehicle itself doesn't have to be that high. So we then started developing the end effector and tried to inspire ourselves how people usually write. We ended up with the design you can see here in the image. It incorporates 4 key features. The first one is compliancy, which we basically added by building the platform as a passive Gauss-Stewart platform. That's a 6 degree of freedom end effector that consists of 2 bodies, a static lower one, and then a freely moving upper body. Both of them are connected by 6 spring dampers. For such a passive Stewart platform, the motion and the compliancy of this upper part actually highly depends on the geometry of the end effector itself, and we therefore try to optimize this such that the end effector counteracts disturbances by always trying to move the upper part back to its center position. If you look at the plots which show the energy required to displace this upper part, you can actually see that this is not always given. For our optimized geometry at the top, we have a nice basin of attraction at 0, 0, shown in green, surrounded by higher energy levels in blue, whereas for a Stewart platform with equally sized upper and lower body, you can see that less energy is required the further the upper part moves outwards, which would make it always fall to the side. So we then also added 3 Swedish wheels to the top so that we have multiple contact points. Each of those wheels is actually actuated by a servo motor, making this whole upper part basically an omnidirectional ground robot that you can compress against the ceiling. And then we also added an upward-facing camera looking at a checkerboard pattern so that we know where this upper part is relatively to the lower part. Here you can see the full system in action. So we have the drone basically compressing the end effector against the ceiling, and then both of them are tracking the same trajectory, which is a circular one in this case here. So as part of this work, we also then did an ablation study to evaluate the impact on precision of every design choice we made. For that, we manufactured a set of dummy components as drop-in replacements for the actual parts. And then we did different experiments with different combination of the end-effector. So to actually remove the multiple contact points, we built a single point of contact rigid end-effector. We also had rigid rods as a replacement for our spring dampers. And then we also used dummy servos with bearings so that we have freely turning wheels. Additionally, we then also ran our end-effector in an open loop fashion. So here's a table with the results from the experiments. Let me just highlight a few of them. So in free flight, our aerial vehicle had a mean absolute error of roughly 2 centimeters, and only by adding multiple contact points and pushing against the ceiling, we actually were able to almost halve that. By then additionally controlling the motion of the end-effector along the ceiling, we actually found out that the rigid end-effector is almost as precise as our full compliance system, and this showed us that actually compliance is not necessarily the key factor for precise aerial manipulation, but rather the right contact with the environment. This is somewhat counterintuitive, especially when you do research with drones, because we tend to see objects as something we should normally avoid. But the study actually showed us that in order to do aerial manipulation very precisely, we should not shy away from contact, but rather try to exploit it. So to conclude, in this work, we tried to develop an end-effector for aerial layouting, and we managed to achieve state-of-the-art precision. We did this by carefully choosing, evaluating, and optimizing the individual end-effector components. And during the development, we actually found out that that if you exploit or exploiting the contact with the environment is actually one of the key factors to improve precision during aerial manipulation. Yeah, so with that, I would like to thank you all for listening, and I hope to see you at the poster session later so that we can go a little bit more into detail of this work.
So now is the time and our opportunity to ask questions to the speakers. And we are going to set it up also so that we have the online presenters joining us. So time for questions.
Hi, I have a question about the reduced order linear models paper. So my question is, how did you decide the dimension of your lower dimensional linear model? Because I would imagine that in theory, as you increase that dimension, you would get a better and better linear fit. Oh, sorry, I think you're muted.
So, yeah, just one moment. You're muted and we cannot hear you. Let's try again. Can we hear you?
Can you hear me now?
Yes.
Oh, nice. Okay, let me go with the question. Thanks for the question, very good questions. So we actually have details in the paper, but to be short, is that we first go with a very, assuming it's a high dimensional, systems, like 10 order stuff. And then we do linear fitting, and we find the systems, and then we do model reductions by looking at Hancock singular values. Because we want to balance the models, don't want to, if we higher order, because if we increase orders, the fit will be good, but it won't be that linear increase will convert to some values. So we want to cut off the orders. So basically, we pick up the most, we just look at Hancock singular values to pick up the optimal dimensions of the systems.
Okay, thank you.
Okay, we have another question.
Yeah, I have a question for the End-Effector paper. Are you localizing the area vehicle with a Vicon system, or are you using other methods?
Yeah, so actually, all of the experiments we did, so we had ground truth for the aerial vehicle, which we used to move it, and then the end-effector actually, it was very hard to get the position because it was occluded by from the top from the aerial, from the bottom from the aerial vehicle, and from the top from the ceiling. So we actually then used the ground truth from the aerial vehicle, and then the upward-facing camera, which were tracking this upper part. And then we did also experiments to see how actually accurate the camera tracking by itself is, which was below 1 millimeter actually.
All right, thank you. Do you think the maybe like you can use the odometry of the wheels to like better localize?
Of the what? Sorry.
Of the wheels to better localize the vehicle.
Yeah. So. Yeah, you maybe could. I don't know if that works since they're omni. Yeah, maybe you could actually. Yeah. So I don't know if the servos which we use, they're quite lightweight, and I don't know if they're accurate enough. Usually, you don't get such a good feedback from them. But yeah, so I mean, in general, it's something we want to look at now, how to actually get rid of the Viken system or the motion capture system.
Thank you.
One more question from the audience?
Yeah, I have a question about the multi-objective ergodic search. So first we formalize the problem into a multi-objective problem, and then we scalarize it using adaptive weighting mechanism. And it seems like the weights are important. So how do we set these weights?
Okay, so the question is how we set the weight. So normally we will begin with, a user-defined initial guess or just some random initial guess. And then we will run breadth-first sampling in the transformed weight space. So basically, we will cover the entire weight space so that we can get, different options, different trade-offs in the entire Pareto-optimal front.
So it's application-dependent, the weight.
Okay, that's an excellent question. So in real-world application, so twofold. First, we believe with the Pareto-optimal front, then the decision maker can actually have a better understanding of the task and pick the one that match his preference. And secondly, far away in the future, we think it's a very promising direction to leverage machine learning to learn, to mimic those decision makers' preference, so that those highly nonlinear preference can be captured and automatically select the best solution from the Pareto-optimal set.
Thank you.
Well, perhaps I'll ask one last question to one of our online presenters on data augmentation for manipulation. So Peter, you had multiple things that you augmented over. Do you have an ablation of which aspect matters the most in order to improve performance?
So by that, do you mean the different terms in the objective, or?
Yeah, and like you had the robot and the environment.
I see. So we don't have ablations in the paper over whether to augment the environment or not, whether to augment the robot or not. We only test augmenting both the robot state and the moved object state. The intuition there being that for manipulation, typically you care about what's moving. So if it's stationary, augmenting over the stationary thing may not improve either predictions or recognition or whatever the actual downstream task is. But if that was true for your task, then I suspect that you could keep a lot of the objective terms and just apply them to the stationary objects, or if for some reason you really didn't want to augment the robot state, you could basically just not do that. But it would probably be task dependent.
Great, thank you. Let's thank all of the speakers. Now we're going to have a long talk by Matthew Cavarsi from Harvard University on multi-robot adversarial resilience using control barrier functions.
Is there a reason nothing's coming up? Okay, hello everybody. My name is Matthew Cavarsi and I'll be presenting our paper for RSS. In this paper, we use control barrier functions to satisfy multiple different objectives simultaneously. One of those objectives is resilience, which models a physical constraint on the team formation. And we notice that when the team formation is restricted in this way, it becomes more difficult to navigate through cluttered environments, and so we analyze some of the different scenarios where this may occur. Robot teams satisfying multiple objectives is a common but important problem. Control barrier functions are formulated as an optimization problem that takes these different objectives as constraints and looks to find a control vector that satisfies all of them. As an example, I will put our methods into the context of a flocking problem, where different objectives are to navigate across an environment, agree on a heading direction to move, while also avoiding collisions and maintaining a resilient formation. Now, as I mentioned, the addition of a resilience constraint, which attempts to fortify the team's communication network to protect it from vulnerabilities, will be the main focus of this work, as its inclusion adds new interesting challenges for control barrier functions. We assume that robots can communicate with each other if they're within a certain distance r from each other, allowing them to form a network such as the one shown here. However, malicious robots within the network may be able to compromise the performance of the team by tampering with the information they relay to others. We'll assume that malicious robots can only perform attacks on information, but still follow the other objectives of the team, so as to not be easily detected. As a motivating example, we show what a successful attack can look like. The arrows below the robots here correspond to the heading direction that they share with the rest of the team. As the robots start to move, they begin a linear consensus protocol, as shown by the plot on the left, and eventually converge on a heading value. As the network becomes sparser, the adversary can perform an attack by broadcasting different heading directions to different robots. This causes the team to physically split apart and the flocking to visibly fail. As I mentioned, this is due to the fact that the network becomes too sparse such that all the information has to flow through the adversary. This motivates us to build networks that are resilient, meaning that there are multiple paths of communication between any two robots. Previous works have shown that there are certain topologies that guarantee this resilience to adversaries, and a common theme among all of them is that resilience is related to a network that's well connected. Since we model the connectivity between robots as a function of distance, we can actually impose resilience as a physical constraint by enforcing that robots stay close enough together to form a well-connected network. Control barrier functions have been widely used to take multiple different constraints and satisfy all of them simultaneously. By formulating resilience as a physical constraint, we can now actually include it under the same framework with the other physical constraints such as collision avoidance. However, this introduces new challenges, as the resilience constraint can sometimes be at odds with the other constraints. To explain more about this, I will start by giving more detail about the control barrier function framework. The basic idea behind control barrier functions are that the robots look to minimize the difference between their input and desired input UDES, which usually encodes the main navigational objective of the robot team. While minimizing the difference between their input and the desired input, they also look to satisfy several constraints. In our paper, we consider resilience constraint as well as safety constraints. For the resilience constraint, we look at the algebraic connectivity of the network, which quantifies how well connected the network is. Previous works have shown that if the algebraic connectivity is at least 4f, where f is the number of adversaries in the network, then resilient consensus can be guaranteed. And so we set this as our resilience constraint. To deal with collision and obstacle avoidance, we set safe distances dmin-c and dmin-o and require that the robots respect these distances. Now, ideally, a CBF can handle all of these constraints simultaneously, but sometimes it can be difficult for the robots to maintain a close-knit, well-connected formation while navigating through certain environments. In these cases, the environment forces a trade-off between resilience and navigation. In this paper, we look to characterize when this happens and determine how to handle it. How we deal with the trade-off between resilience and navigation is often problem-dependent. Ideally, we want to treat resilience as a hard constraint, where it could be guaranteed to be satisfied. A key challenge here is to characterize some of the different scenarios where resilience may be compromised. For example, we look at a scenario where robots must navigate around a large obstacle, and we looked. For example, we look at a scenario where robots must navigate around a large obstacle, and we look to find the largest such obstacle that robots can split around it without losing resilience. However, there may be times where the environment makes it impossible to navigate in a resilient formation. For example, if the robots were to encounter a narrow corridor, they would be unlikely to fit through it without the formation breaking down. In these scenarios, we derive an alternative control barrier function, along with some critical control parameters to allow the robots to break down resilience and treat resilience as a soft constraint, which means that resilience will be compromised if necessary to allow for navigation to continue. Finally, I will conclude my talk by showing some example experiments where the robots encounter some of these different scenarios to show how well the theory that we developed aligns with actual real implementation. But first, I will talk in more detail about resilience as a hard constraint. As the robots navigate around a large obstacle, they may split around the obstacle to opposite sides. Since we model resilience as a function of distance, when the robots split around an obstacle, the resilience may be compromised. As shown by the plot of algebraic connectivity on the right here, approaching the resilience threshold of 4f plus epsilon. In this case, the resilience will try to pull the robots back together, while the obstacle tries to push them apart, and the desired input tries to push them forward, causing the team to get stuck. This motivates us to characterize a critical size such that the robots can navigate around the obstacle without losing resilience. To do this, we look at the distance that the robots must separate from each other if they were to navigate around the obstacle to opposite sides. Then we consider all possible formations where some number of robots I and n minus I make up the two groups, and we find the lowest algebraic connectivity of all these different formations. Then we look at the distance that's sufficient for this worst case formation to still maintain resilience, and we set this as our critical obstacle size, DO max. The DO max that we derive is shown here, and we show it to be a function of the resilience threshold, the number of robots, and the communication radius of the robots. This slide uses simulations to verify the theory from the previous slide. In the top plots, what we do is we set the obstacle size to DO max, and we show that the robots, which are shown by the little blue circles, are able to split around the obstacle while maintaining resilience. However, if we increase the obstacle size just a little bit, like in the bottom plot, the robots no longer can maintain resilience while splitting around the obstacle, and so they get stuck behind it, as the theory predicts. Next, I will talk about resilience as a soft constraint. Take, for example, the narrow corridor scenario. In this scenario, as the robots try to navigate through a narrow corridor, the formation starts to break down and resilience may be compromised, as again shown by the algebraic connectivity plot on the right, approaching the resilience threshold of 4 plus epsilon. In this case, the resilience input will try to drive the robots back out of the corridor, while the desired input tries to push them further through it. Because of this, it may be impossible for the robot team to make it through the corridor while maintaining a resilient formation. This motivates us to redesign our CBF to take resilience as a soft constraint. We call this the nested CBF approach. The intuition here is there's an inner CBF that minimizes the difference between the robot's input and a desired input while satisfying the resilience constraint. Then the solution to this inner CBF is fed to an outer CBF, which minimizes the difference between this new input and a final input while satisfying the safety constraints. In this way, the safety constraints are guaranteed to be satisfied, and the resilience constraint will be satisfied as much as possible. Now, we notice that the robots don't always compromise enough resilience to navigate through any corridor, and so we also include a gain term denoted by gamma in the inner CBF. This motivates us to determine a maximum gain such that robots will always compromise resilience in favor of navigation. To do this, we again look at the worst case formation that can arise, which in this case is that when robots form a path graph. We find the algebraic connectivity of this path graph formation and the resultant control vector that will look to try to improve the resilience. We compare this to the desired input pushing the robots the other way and choose a gain such that the desired input is greater than the resilience input. The maximum gain value that we derive is shown here, and we show it to be directly proportional to the resilience threshold and inversely proportional to the desired input. Shown here is a simulation that shows the existence of a gamma critical. Now, gamma critical is an empirical value for a particular narrow corridor that shows essentially if gamma is greater than gamma critical, the robots will be able to compromise resilience and move through the corridor, whereas if gamma is less than gamma critical, then the robots get stuck in the corridor. We show that our gamma max that we derived is greater than the gamma critical, and so the robots are able to navigate through the corridor. Finally, I would like to show some experiments where the robots encounter some of these different scenarios. This first experiment shows an obstacle size that's small enough such that the robots can split around it without losing resilience. In this experiment, as shown by the plot on the right of algebraic connectivity, the algebraic connectivity always remains above the 4f plus epsilon resilience threshold, and so the robots are able to navigate around it safely. In this scenario, the robots use the nested CBF approach to navigate through the narrow corridor. As shown again by the plot on the right, the algebraic connectivity now actually drops below the threshold as the robots compromise resilience to make it through the corridor, and then it moves back above it as they reconvene on the other side and regain resilience. Finally, I'd like to circle back to the resilient flocking example from the beginning. In this example, the arrows below the robots correspond to the heading directions again, and they all choose a heading direction and must share and agree on that value. The heading consensus will be plotted on the left-hand side, and the algebraic connectivity will be plotted on the right. The adversary, highlighted in red here, will try to choose a heading direction to try to drive the robots towards the right side wall. Now you'll see that since the algebraic connectivity is greater than the threshold, as the robots move across the test bed, they are able to maintain a resilient consensus despite the attack and travel across the test bed as a unit. Thank you so much for listening, and I'll be happy to take any questions now.
So we have a few minutes for questions. Well, let me start. So I think you mentioned in the hard constraints that you are modeling resilience as a function of distance, right? But communication is also dependent from many other factors. You know, there could be multipath effects, it could be a body of water that affects that. Have you thought of alternative ways that you can have, more, taking this factors into account, or perhaps monitoring the quality of communication that's affected by them?
Yeah, so that's a good question. So in this paper, we model resilience, we model connectivity as a function of distance, because with the distance, we can quickly optimize the communication by telling robots to move closer to each other. If we were to consider other things, such as maybe obstacles that occlude the communication from happening, then we would have to kind of formulate the connectivity as a connected graph, which makes it, or a directed graph, which makes it a little more difficult, but could be an area for future work, as well as, you know, like packet drops, something like that. We can model the communication as something that's a probability, but then the whole notion of resilience is a little bit more difficult, because we have to make sure, we have to basically say, like, in expectation, the network is well connected, or something along those lines.
Hi, great talk. I just have a quick question regarding the number of adversarials in the network. Have you guys studied sort of like a ratio of like the maximum ratio of the number of adversarials possible in the network to keep resilience? Thank you.
Yeah, good question. So the algebraic connectivity is limited to n, which is the number of robots. And so since we require the algebraic connectivity remains at least 4f plus epsilon, then naturally we can only have up to 1/4 of the network be adversaries. Most of the examples we showed here only include one adversary, but that was only a limit of hardware, because you need more robots to have a greater resilience to more adversaries. So generally the only restriction is that only 1/4 of the network can be adversaries, and beyond that, f can be whatever we choose it to be.
Thank you.
Other questions?
Hi, great talk. So I have maybe a little bit of a forward-looking question of what would change if the adversary was allowed to take arbitrary actions in addition to passing arbitrary information? And could the CBF be used to detect which robots are acting adversarially?
Yeah, so actually it becomes a lot easier to detect when adversaries are performing actions in this way by using the CBF, because the CBF computes the control input for all of the robots. So each robot has an expectation of what the other robots around them are going to do, and can quickly observe that one of the robots isn't following what it should be doing. So in that way, that's why I said it would be easy to detect an adversary if it were to behave differently. In the sense of if it were trying to behave differently to try to affect the team's performance, there have been papers that have looked at some of these kind of problems. And the idea here is to kind of just assume that the robots are going to do the worst possible thing they can do, and choose your strategy around maintaining resilience while that's occurring.
All right, thank you.
Mm-hmm.
Great. Let's thank Matthew.
Thank you.
And the last talk for this session is titled Autonomously Untangling Long Cables from UC Berkeley.
Good morning, everyone. I'm Justin, and I'm here with Vainavi and Kaushik from the Autolab at UC Berkeley, and we're going to present our work on autonomously untangling long cables. So if you're like me and you pack your luggage like this, maybe when you arrived at RSS, you were greeted with a view of a tangled cable, and you had to fumble with it to unpack the clothes beneath it. And although humans do this almost automatically, this is actually a really interesting problem for roboticists to study. Because it's a very challenging state estimation problem, there are very complex dynamics which make it difficult to simulate, and the cable often extends far outside the reach of the workspace of the robot. In addition, there are many practical benefits of household manipulation. There's lots of great related work on 1D deformable object manipulation, including exploring dynamic actions for efficient manipulation, or leveraging approximate models during planning, or learning visual dynamics models from experience. In addition, there's lots of work on untangling, for example, using key points to predict grasp points, or using analytical state estimation to produce viable actions. The focus of this work is really pushing the limits of how long the cables we can handle are. Asking the question of, like, can we use cables that are realistic in household settings up to 3 meters in length? Using these types of cables have a lot of unique perception challenges, where these two cables are the exact same topological configuration, but visually, the right side is almost imperceptible and the left is trivial to see. In addition, even minor changes in the cable state can drastically change the visibility. For example, this knot on the left is completely obscured by the pile of slack on the right if it's moved by a small amount. There's also a host of challenging manipulation problems. There's a high degree of precision required for this task, where the difference between a successful grasp and a failed grasp can be on the order of millimeters. In addition, the workspace of the robot is extremely limited compared to the size of the object, and because of the stiffness of the cable, it tends to form these tricky loops which are difficult to remove and can snare the grasp. So the goal of our system is to produce a system which can go from a cable state on the left, which is tangled with knots, and unknot it into a nice state on the right. So for some intuition on what some initial configurations looks like, here are some visualizations. To make this a little bit more formal, our goal here is cables with at most 2 figure-8 or overhand knots, and our goal is to remove all knots and then verify that all the knots have been removed. If you want some more formalism, you can think of this as defining an indicator function over the length of the cable, and our goal is to make this indicator 0 everywhere. So now I'm going to briefly discuss the system design of the physical system design. We use a Yumi robot, which is a bimanual collaborative robot with 7 DOF arms and parallel jaw grippers. To each of these grippers, we attach custom gripper designs with little teeth at the bottom, which we call cage pinch jaws. And the cool thing about these cage pinch jaws is that they allow dual grasp modes. On the left, we have caging, which constrains the cable within the jaws while allowing it to slide laterally along the cable. While on the right, if we just pinch harder, we can constrain the cable completely within the fingers. We use an overhead depth camera, which has grayscale and very accurate depth at a low frame rate, an example point cloud of which is on the right. And here's a visualization of our foam padded surface for safety of the robot, and as well as the observable region marked. And here we visualize the reachability of the left and the right arms respectively. Notably, you can see that the size of the cable is large enough that even in compact configurations, it can reach outside the workspace. And now we're going to present the software system to handle this task, which we call sliding and grasping for tangle manipulation, or more affectionately, SGTM.
Okay, so I'll begin by introducing the manipulation primitives used by SGTM. First, we have dynamic shaking. This is a primitive used to disambiguate the cable state or reconfigure it into another configuration in the event that it's in a difficult position to perform other motion primitives. Next, we have tracing, which we use as a verification primitive. Once our perception system determines that there are no knots remaining, we want to physically verify this by tracing through the cable using alternating pinch and cage grasps. In the event a knot is encountered, we perform a knot isolation move that's shown in this video, which places the cable down such that the knot is unoccluded and ready to be untangled. Dual cage separation is used for loosening or untangling knots, and in this case, both the jaws are caging the cable. A Reidemeister move, the name coined by the knot theorist Kurt Reidemeister, grasps the endpoints and pulls them to opposite ends of the workspace. This preserves the topology, but makes knot visibility easier. Now introduce the perception system, which enables the manipulation primitives I just discussed. So we train a fully convolutional neural network in a supervised manner to output a heat map over the location of the endpoints of the cable. This is used in Reidemeister moves as well as for dynamic shaking. We use the faster RCNN architecture to learn bounding boxes for knots. This is used as the first step in identifying grasp points for dual cage separation and for also verifying that no knots remain before we perform tracing. We use 2 fully connected networks with a ResNet34 backbone for grasp point selection for the dual cage separation primitive. The first network takes in the image of the knot crop produced by the previous network that I just discussed and predicts the first grasp point. The second network takes that image along with that first grasp point to predict the second grasp point for the dual cage separation action. And the grasp points predicted by this previous network are passed into our planner, which does a joint search over grasp poses to find a pair that is collision-free and reachable. When tracing, we use an analytic method that observes the 3D point cloud near the grippers and analyze whether we've reached a knot. So if the crop of the point cloud directly in front of the grippers has greater than n points, or we see more than one connected component, that means that we've encountered a knot and we terminate tracing and move on to knot isolation. We use the same FCN for endpoint detection used on the full cable image to also determine if we've encountered an endpoint during tracing, which is our indicator that we've fully untangled the cable. So putting together now all the manipulation primitives and the perception system, we present our SGTM algorithm. So first, we check the number of endpoints, and based on that, we either determine to shake, perform a Reidemeister move, or do nothing at all. And next, we perform knot detection to disambiguate the state. And if our perception system doesn't see any knots, we physically confirm this to make sure that we can terminate. And if we are to encounter a knot while tracing, we return to the knot detection step. If a knot is detected, we determine the grasp points and perform dual cage separation to loosen the knot, and then we loop back to our first step.
We now present the experiments that we use to validate the performance of the manipulation primitives, our perception pipeline, and the SGTM algorithm. So we use two primary tiers of cable configurations to validate the algorithm. So the first tier consists of single overhand or figure-8 knots, tier 1, and tier 2 consists of 2 overhand knots, 2 figure-8 knots, or a combination of the two. And we run 12 rollouts to validate our algorithm. Now moving on to some example results. In the first video, the robot detects an overhand knot, and it uses the grasp point networks to predict points for the dual cage separation action. It then runs a shaking action, and then it moves on to tracing to verify that the cable is fully untangled. And once it reaches the endpoint of the cable, it terminates successfully. In the second video, the robot loses its grip on the figure-8 knot as it pulls it apart. But then it shakes, performs a Reidemeister move, and then does one more shaking action. And the figure-8 knot has been sufficiently loosened such that these dynamic motions fully untangle the cable. And then once again, it traces to verify that the cable is fully untangled. The table here shows our results. For tier 1, we have 8 out of 12 rollouts ending in untangling successes, excluding the verification step. And for tier 2, we have 6 out of 12 rollouts ending in untangling successes. As you can see, tier 2 is significantly more difficult, especially because of the longer time it takes to untangle both of the knots in the cable. Now we present some of our dirty laundry, or failure cases that SGTM encounters. In the top left video, the cable leaves the workspace entirely due to failed slack management when we're performing a shaking action. On the top right, SGTM misses a grasp while trying to untangle the cable. But while this is not fatal, it often creates complications due to the cable moving off to one side of the workspace. On the bottom left, the cable actually becomes jammed due to the adapters at the endpoints when SGTM attempts to perform a cage separation action to untangle a knot. And finally, on the bottom right, we can see that the robot actually takes a long time. This is a sped up video, and it often takes a long time to slide along the cable. And we observe that in experiments, there are often false positive knot detections that cause the algorithm to have a low verification success rate. We've also been working on a second version of the SGTM algorithm to address the failure modes and improve upon the current iteration of the algorithm. Currently, we focus on one type of USB cable, but we wish to generalize to more types of cables in the next iteration of our work. And we also plan to use SIM and larger quantities of data to improve the generalization to new types of knot. And finally, our contributions include a problem formulation for the untangling long cables problem, a dual mode gripper design that critically allows for sliding and pinching actions, and we also leverage the unique capabilities of these grippers and combine them with a perception pipeline into the SGTM algorithm and present a unified system, an integrated system that is modular and capable of untangling long cables up to 3 meters in length. Thank you.
And we have again time for questions.
Hi, really excellent talk. I have 2 questions. My first is, if I recall, you said at the beginning something about that you assume at most 2 overhead knots. Is that, what's the reason for that? And my second question is, I missed, how do you decide which of the primitives to execute?
Yeah, thanks for the question. So the first assumption is mostly just for defining our experiment tiers. And so there's a little bit of practicality involved there in choosing what to experiment with. In terms of the second question, I think Bimanual could.
Yeah, so for determining which primitive to use, we use our perception system. So for example, we check the number of endpoints to see if like a Reidemeister move is necessary versus if a shaking action is necessary. And similarly, we also check like, do we see any knots in the scene with the perception system? And if we do, we'll use the dual cage separation action to undo that knot, or else we'll trace. So essentially, our perception system determines, or helps us determine, what's the optimal action.
Great, thanks.
Can you talk a little bit more about your inspiration for these manipulation primitives? You referenced, I think, topological work. It comes mostly from this literature to putting together this system, or perhaps how you've observed people solving these problems?
Thanks. So I think the inspiration for some of the primitives themselves are based on ourselves just playing with cables and noticing that when humans handle long objects, a lot of times we're not statically grasping a cable, but instead we have to slide along the cable. And so we wanted to have some simple mechanical design that allows this without any sensing or closed-loop control. And so we settled on a design like the grippers that we have, which allow us to do these primitives similar in spirit to what humans do.
Yeah, there we go. Yeah, very interesting talk, thank you. I was wondering if you noticed any difference in the success rates depending on where the knot was on the string. Like, was it better at untying knots in the middle compared to the end? Because it looked like it would be harder to grasp if it was right at the end.
Yeah, so we actually, when we ran the experiments, we systematically tried different knot configurations, as in where the knots were located. We didn't notice any significant differences in success rates, but it is significant that a knot is near an endpoint, for example, because you won't have to slide as far along the cable to fully undo the knot. So, for example, in the video where you saw the cable actually coming out of one of the grippers as it tried to untangle, in that case, if that cable were actually closer to the endpoint, it might have already untangled that knot by the time it fell out. So in general, you might expect that knots closer to endpoints would have a slightly higher success rate, but we didn't observe significant statistically, or very statistically significant difference. So.
Okay, cool, thank you.
I appreciated your failure cases. Did you ever generate a knot during the process of trying to a knot?
Yeah, so actually that was one of our failure modes, because if you, even just with primitives that place the cable in certain places and then pick it up at other locations, you can actually tie knots, and we did experience that. And there's obviously a lot of work to be done to mitigate this failure case with improved slack management, because if you manage slack very carefully, then this wouldn't happen, but because of the difficulty and complexity of the problem, it does end up happening. So there's definitely a lot of further work to be done there. Yeah.
Great. Let's thank the speakers.